Hello one and all, welcome to another online video by Einstein Academy. In this video, we'll be looking at some questions that addresses the learning outcomes M and N from the topic of chemical bonding from the JCH2 chemistry syllabus. So in the previous lecture, we mainly looked at learning outcomes M, whereby candidates are expected to be able to describe, interpret, and or predict the effect of different types of structure and bonding on the physical properties of substances. And in this final lecture of this topic, we will be applying what we learned from learning outcome M to be able to suggest the type of structure and bonding present in a substance from given information. So after many lectures, we have finally come to the last learning outcome where we'll finally wrap up the topic of chemical bonding, a very long chapter indeed. Okay, so let's start with the questions. November 2009, paper 1, question 6. What is the property of a solution of dry hydrogen chloride in dry methylbenzene? So the important thing here is that hydrogen chloride is HCl and methylbenzene, of course, you all haven't learned this if you haven't done organic chemistry, but this is the structure of methylbenzene. But the point is that this is an ID-ID type of interactions molecule, but this is, you can say it's a PD-PD type of interactions of molecule, and hence, the important thing here is that HCl won't be able to dissolve in methylbenzene. And as such, because if HCl, right, dissolves in water, it would actually form H plus cation as well as Cl minus cation, and it will be able to act as an acid. Okay, however, if HCl is not soluble in that particular solvent, then it will not be able to ionize to form H plus ions, and as a result, it will not have any properties of an acid. Okay, so again, dry HCl is not soluble in dry methylbenzene because the interactions of the solute-solvent interactions is not favorable enough to overcome the solute-solute interactions and the solvent-solvent interactions, and hence, it does not ionize to form H plus and Cl minus ions, hence it is not acidic. It has a pH less than 7. This is false because we already mentioned that it's not an acid. It is a non-conductor of electricity. This is actually true because of the fact that it doesn't ionize, so there's no ions, there's no charge carriers, and they're not mobile. There are no charge carriers, so obviously there's no mobile charge carriers, so option B is actually correct. It reacts with magnesium to give hydrogen. This is only true if it's an acid and only if it ionizes to form H plus ions, so option C is wrong. It reacts with anhydrous sodium carbonate to give carbon dioxide. This is again true only if it ionizes to form H plus ions. And hence the answer to this question is B. November 2013, paper 1, question 5. Which bonding does not correspond to its description of physical properties? Okay, so if it's giant covalent, high melting point, this is true. Conducts electricity when in solution but not when solid, this is false. Okay, because like in general, giant covalent compounds can't even dissolve in water because as we have talked about, the covalent bonds are actually very strong that cannot be overcome when they form solute-solvent interactions. So number one, it doesn't even dissolve. And number two, even when it dissolves, there won't be charge carriers and hence there won't be mobile charge carriers. And on that count, it's also wrong because it will not conduct electricity. Okay, for simple covalent structures, low melting point, that is correct, does not conduct electricity in any state. This is also true because of the fact it does not contain any mobile charge carriers. Metallic bonding, variety of melting points. Okay, this is a bit ambiguous because like variety just means like different, right? But I guess in this case, what it's trying to say that it can vary from very big to very high to very low melting points. So okay, so let's just keep this. This is, I guess, a bit of a bad wording, but let's just put this aside for the time being, and then we will see whether there's a better answer to option B or not. Okay, it conducts electricity when solid and when molten. This is definitely true because it has a sea of delocalized electrons, whether be in the solid state or in the molten state. Ionic compounds have high melting points. This is true because of the strong electrostatic forces of attraction between oppositely charged ions that require a lot of energy to break. It conducts electricity when molten. This is true because now the charge carriers, which are the ions, are broken down from the lattice structure and are free to move within the liquid. Not in solid, this is also true because in the solid state, the mobile charge, the charge carriers, which are the ions, are vibrating only about their fixed positions and they're not mobile. So option D is true. Okay, this is true. This is true. And this, with the exception of the variety of melting point, which is a bit ambiguous, but definitely like giant covalent compounds do not conduct electricity when in the solution. So this is definitely false, and hence we have to say that C is true, and the answer for this will be A, because the question is does not correspond. Okay, in MCQ, we choose the best possible answer. November 2015, paper 1, question 4, the melting point of calcium, 839 degrees Celsius, is much higher than the melting point of sodium, which is only 98 degrees Celsius. Which statement is most relevant in explaining this difference? So first, we have to understand what type of structure it is. Both is metal, so it's giant metallic lattice, and what are the factors that influences the metallic bond that will cause a variation in melting point. The factor that causes a variation in melting point of metals is the charge density of the metal. Okay, so basically like Ca2 plus over the radius of Ca2 plus versus the radius, the magnitude of the charge in Na plus versus the radius of the Na plus cation. Okay, so the calcium ion is larger than the sodium atom, and this is indeed true because like calcium is actually below sodium in the periodic table. So the radius of calcium is actually larger than that, and actually if the radius is larger, right, it would actually contribute to a weaker metallic bonding, which would actually result in a lower melting point. But as we can see, calcium actually has a much higher melting point than sodium, so the radius does not contribute to this difference. Okay, does not explain this difference, so A is wrong. The calcium atom is heavier than the sodium atom. If you look at the charge density, nothing says the factor of mass does not contribute to the strength of the metallic bond, and hence it also doesn't contribute to the how high or how low the melting point is. So B is also wrong. The calcium ion has a higher charge than the sodium ion. This is true because like it's 2 plus charge versus 1 plus charge, and indeed the metallic bond is proportional to the magnitude of the charge, and calcium having a higher charge will indeed have a stronger metallic bond than Na plus, and which would cause it to have a higher melting point of 839 degrees Celsius as compared to 98 degrees Celsius. So option C is the answer. If we look at option D, the calcium ion contains more electrons than the sodium ion. Again, the number of electrons is not relevant to the charge density, and hence it does not affect the strength of the metallic bond, and it does not affect the melting point. November 2010, paper 1, question 32, a simplified structure of a molecule of chlorophyll is shown. Okay, so the magnesium atom is in the middle. So if we look at this nitrogen atom, right, it's actually doubly bonded. So there's 2 electrons here on the nitrogen atom, and there's 1 electron here. And hence, right, there is 2 remaining electrons because nitrogen is in group 5. So this bond between nitrogen and magnesium, and between this nitrogen and this magnesium similarly, is actually that of a dative covalent bond, whereby the nitrogen uses both its lone pair of electrons to form a dative covalent bond with the central Mg2 plus cation. Okay, so this nitrogen on the other hand has 1 electron here and 1 electron here in the covalent bonding, and in fact it actually has like okay, so 1, 2, 3, 4, 5. Okay, so this 5 electrons belongs to nitrogen, and this triangle is actually a negative charge that came from the Mg cation. So Mg loses 1 electron to this nitrogen and also loses 1 electron to this nitrogen, and in doing so, this Mg will form a 2 plus charge and this nitrogen will form a 1 minus charge. And this interaction between this N and this Mg is actually that of an ionic bond. Okay, so out of the difference between this is that because this nitrogen is already bonded to 3 things, so the remaining 2 electrons, this is a normal dative covalent bond. But because this nitrogen is only bonded to 2 things, so in order for it to have octet, it actually accepted an electron, and in doing so, it formed an N minus N ion. And the interaction between this N minus and this Mg2 plus is that of an ionic bond. Furthermore, in the question, it says that the magnesium atom is situated in the center of a planar arrangement of nitrogen atoms. Okay, so what does this structure suggest about the nature of the bonding around the magnesium atom? So dative covalency, this is already true. As we've mentioned, one of nitrogen uses its lone pair to form a dative covalent bond with the central Mg2 plus cation. And in the dative covalent bond is a sigma bond. Because it's a single bond, so it's definitely on overlap. On the other hand, sp3 hybridization, this is false because they tell you that the magnesium atom is in the center with a planar arrangement. if it's sp3 hybridization, this Mg, the arrangement around this central Mg2 plus will actually be that of a tetrahedral arrangement instead of a planar arrangement. And hence, option 3 is wrong. And only 1 and 2 is correct. And therefore, the answer to this question is option B. Okay, November 2015, paper 1, question 32. From the position of the elements present in the periodic table and the physical properties of the compounds, which compounds are covalent? Okay, so if you look at option 1, right, first of all, if you look at all the atoms, they are all non-metals, and hence it can only be covalent bonds. Okay, and from the boiling point, we can see it's also not very high, and hence, definitely option 1 is a covalent compound. Option 2, germanium chloride. This germanium is actually in group 4. Okay, and group 4, again, it's a non-metal. Sorry, group 4 is like that. Okay, so it's also a non-metal, and non-metal is also a covalent compound, and the boiling point is also not high. And this further reinforces the fact that GeCl2 is a covalent compound. For option 3, right, AlBr3 is between a metal and a non-metal, and bondings between metal and non-metal is in general ionic. However, we have discussed that AlCl3 is a covalent compound because of the fact that the Al3 plus has a very high charge density, and it actually polarizes the electron cloud of the Cl minus to a large extent that the AlCl3 goes back to being a covalent compound. If we were to compare the polarizability of the Br minus N-ion and the Cl minus N-ion, the Br minus N-ion is actually larger than that of the Cl minus N-ion. And since the larger size means that the attraction between the nucleus and the valence and the electron cloud, right, is actually not so strong. The distance between the nucleus and the electron cloud is longer, so it's not able to hold on the electron cloud as well as Cl minus. So if Cl minus is polarized already by the Al3 plus to be a covalent compound, certainly the Al3 plus will also be able to polarize the electron cloud of Br minus, in fact, to a larger extent. And certainly AlBr3 is also a covalent compound. It's also a covalent compound. And the boiling point of 265 degrees Celsius is also not very high. And it is also true that AlBr3 is a covalent compound. So the answer to this question is option A, whereby all three selections are true. They are all covalent compounds. November 2011, paper 2, question 4b. Among the elements of group 4, those towards the top, carbon to germanium, have very different properties from those at the bottom, tin and lead. So for example, the melting points show a marked change after germanium. And the question is that carbon, silicon, and germanium all form a solid with the same type of structure. What type of structure is present in solid carbon, silicon, and germanium? So for carbon, we already know that they form giant molecular structures within carbon atoms. And the two structures are basically graphite and diamond that we covered. So definitely, if they tell you that it's the same type of structure between carbon, silicon, and germanium, this is giant molecular structure for sure. Okay, and the second part of the question suggests why the melting points of these elements decrease from carbon to germanium. So if carbon, silicon, and germanium are all giant molecular structure, then what are the factors that decide on how high the melting point is? And the thing is that, so you need to hold in mind what is the thing that you're breaking during melting of giant molecular structures, and the answer is the covalent bonds. Okay, so the CC covalent, so we're comparing between the CC covalent bond, the SI-SI covalent bond, and the GE-GE covalent bond. And the size of carbon is actually smaller than that of silicon and is smaller than that of germanium because germanium is below silicon in the periodic table. And similarly, silicon is below carbon in the periodic table. So the bond length of CC bond is shorter than that of SI-SI, which is shorter than that of GE-GE. And hence, the covalent bond of CC is the strongest, followed by SI-SI, followed by GE-GE, and hence the melting point is also in the same order, in the sense that you need the most energy to break the strongest CC bond, and hence it has the highest melting point. You need the smallest amount of energy to break the weakest GE-GE covalent bond, and hence germanium has the lowest melting point among the three. Okay, that's the answer for part B, why the melting points decrease from carbon to germanium. Because the strength of the covalent bond decreases from carbon to germanium based on their bond lengths. November 2013, paper 2, question 4b, describe the structure and bonding in calcium with the aid of a label diagram. So what you can do is you can draw the cation of Ca2+, then the cation of Ca2 plus like this in a ionic, sorry, not in a giant metallic lattice. Okay, so of course you can only draw part of it. So you can draw it like this. Then Ca2 plus. Okay, so this is part of the ionic lattice. So we can draw one more to make a cube. Okay, and then you can put many electrons in the middle to indicate there is a sea of delocalized electrons within the structure. Okay, so that's the answer to part A. Okay, describe the structure. It is made up of Ca2 plus cation in their fixed, vibrating over their fixed lattice points with a sea of delocalized electrons within the entire structure. Suggest why the melting point of iron is significantly higher than the melting point of calcium. So again, these are comparing between two metals, and it is the charge density that is relevant. So we have not covered really transition metals, but what can be said about transition metals? So for calcium, right, this is definitely Ca2 plus and the magnitude of the charge is 2 plus. But for transition metals, they generally can form higher charges. And if they can form higher charges, the charge density of iron will generally be higher than that of calcium, and the metallic bond will be stronger in iron as compared to calcium. And that's the reason why the melting point of iron is significantly higher than that of calcium. Okay, so again, it's going back to the factors that influences the metallic bonding, which is the charge density. Some ionic radii are listed in the data booklet. State and explain the differences between ionic radii of Na, Si, P, and Cl. So for Na, the ion of Na is Na plus, for silicon is Si4 plus, for phosphorus is P3 minus, and for chlorine is Cl minus. And they are all in the same period. So if we were to compare the radius of this and this, right, we would notice that this one actually has, this two actually has one less principal quantum shell. Okay, because it has actually lost the outer principal quantum shell. Principal quantum shell. Okay, and that's the reason why the ionic radius of Na plus and Si4 plus is much, much smaller than P3 minus and Cl minus. If you were to compare the ionic radius of Si4 plus, it will be actually much smaller than that of the radius of Na plus, and that goes back to the knowledge that we learned from atomic structure, because because Na plus and Si4 plus, they are isoelectronic, meaning that they have the same number of electrons. Alright, so the thing is that Si4 plus actually has a greater number of protons, and the shielding effect of Si4 plus is the same as compared to Na plus. So the number of protons being greater in Si4 plus means that the effective nuclear charge in Si4 plus is much, much larger than that of Na plus, and hence it will pull the valence electrons much closer towards the nucleus in Si4 plus as compared to Na plus, and hence the radius of Si4 plus will be much, much smaller as compared to the radius of the Na plus cation. For P3 minus and Cl minus, again, is the same. The radius of Cl minus is smaller than that of the radius of P3 minus. Again, is because they are isoelectronic, so the screening effect is the same. However, chlorine has a greater number of protons as compared to phosphorus, and the effective nuclear charge of chlorine is actually higher than that of phosphorus, and hence chlorine valence electrons will be put tighter to the nucleus as compared to the phosphorus 3 minus anion, and hence the radius of the Cl minus anion is smaller than that of the phosphorus 3 minus anion. Okay, also, these four elements also differ greatly in their melting points. Describe how their melting points differ and explain this variation. So Na plus and Si4 plus, this is giant metallic structure, and the forces that hold the Na plus and the Si4 plus in, oh sorry, not Si4 plus, I'm sorry. So for Na, it's giant metallic, this is giant metallic structure. Okay, so there's strong electrostatic forces of attraction that holds the Na plus in the lattice position, the strong electrostatic force of attraction between the Na plus cation and the sea of delocalized electrons. So it's strong, so the melting points of Na, metal, it's high. For silicon, this is giant molecular structure. Okay, and for giant molecular structure, when you want to melt it, you have to break the strong covalent bonds between the Si-Si atom, and it will require a tremendous amount of energy, and hence the silicon is expected to have the highest melting point among all four. For phosphorus and chlorine, they are simple discrete molecules, Cl existing as Cl2, while phosphorus existing as P4. So if you were to, and these two are held together by weaker ID-ID interactions, and hence the melting point are much, much lower as compared to the metallic bonding of sodium and the covalent bond in silicon. Okay, so they are much lower melting point. And if you compare between P4 and Cl2, for P4, the electron cloud, the relevant thing to compare between P4 and Cl2 is that the electron cloud of P4 is greater than the electron cloud of Cl2. Okay, because like P4 has more electrons. And hence, the ID-ID interactions in P4 is stronger than that in Cl2. And hence, the melting point of phosphorus is expected to be higher than that of chloride. Okay, so that's the answer for this question. November 2013, paper 3, question 3b. The structures of oxides can be simple or giant, and their bonding can be covalent or ionic. Use these terms to describe the structure and bonding in each of the oxides W, X, Y, and Z, and explain your reasoning in each case. Okay, so as we can see, for the melting point of oxide W is 2850 and it's quite high. Okay, so this is like pointing towards the fact that it's either an ionic oxide, because for ionic oxide, it will be ionic bonding. Sorry, in metal oxide, better term for this is metal oxide, this will be ionic bonding. If it's a non-metal oxide, okay, then there are two possibilities. It can either be giant molecular structure, or it can be simple discrete molecule. Okay, so this has high melting point, so it's either one of these two. The electrical conductivity is good when it's molten, so it's pointing to the fact that it's ionic bonding, because ionic compounds conduct electricity in the molten state but not in the solid state. The reaction with H2O is very little, but I'd just like to remind you that for metal oxide, right, when you throw it into water, it will actually form a basic oxide. This is something that is covered in O-level chemistry. But for a non-metal oxide, generally, when you throw it into water, you actually form an acidic oxide. Okay, so the fact that there is actually, the reaction with water is very little, but not totally zero, not totally none, is indicative, again, pointing towards the fact that it's actually a metal oxide of ionic bonding. Okay, so the resulting pH is 8, which is also consistent with the fact that when you throw a metal oxide into water, you get a basic oxide. So definitely for oxide X, this is an ionic type of bonding, and it's actually a metal oxide. Okay, so the structures of this oxide is giant ionic structure. And so let's see. So giant ionic structure, and it's ionic. Okay, for W. For X, the melting point is still significantly high. The electrical conductivity of molten is poor. Okay, so this basically points towards the fact it's giant molecular structure. Melting point is high, it's either this or this, but it does not conduct electricity when molten, so it's pointing towards the fact it's giant molecular structure. Moreover, the reaction in water is totally none, and the resultant pH is 7. So definitely this is giant molecular structure, and it's covalent bonding, okay, because it's between non-metals and non-metals in giant molecular structures. For Y, the melting point is 1280. The electrical conductivity when molten is good, and the reaction with water is very exothermic, okay, and it forms a very alkaline solution. So all this, high melting point, good electrical conductivity when molten, is all pointing towards ionic bonding. Good reaction with water, forming a alkaline solution, means that it's giant ionic lattice. Okay, so giant ionic lattice. This is also giant ionic lattice, and this is, of course, ionic. Okay, for the last one, the melting point is significantly much lower than the rest of the three. The electrical conductivity when molten is poor, so this is pointing towards the fact it's a simple discrete molecule. And moreover, when you throw it into water, you form an acidic solution. So all this is showing that it's a simple discrete molecule and that the type of bonding is covalent. Okay, so that's the answer for this past year A-level question. Okay, so with that, we have gone through all the questions that addresses this learning outcome M from the topic of chemical bonding from JCH2 chemistry. So I hope that you like this series of videos that went through chemical bonding, a very long series of lectures indeed. Hopefully you now have a better idea of chemical bonding from the JCH2 chemistry syllabus. If you like the video, please hit the like and subscribe button, and probably the next set of lectures will be looking into ideal gas, okay, the gaseous state. So again, if you like the video, please hit the like and subscribe button for me to make more videos like that to benefit students out there. And stay tuned again, and I'll see you again for another episode of videos by Einstein Academy. Thank you and see you all.